Um, Thanks everyone for joining us today. Another episode of vLLM Office Hours, number 52 this time. Really good to be back. Sasha is enjoying a nice time away, so I'll be taking over everything for him. But rest assured, he's in the background doing his magic. If you're not familiar with me, I'm Michael Goen. I'm a senior principal engineer at Red Hat AI on the inference optimization team. I've been a core maintainer on vLLM for over 2 years. Sasha and I, host and run these office hours for you. Today we have two guests. Christopher Newland, Chief AI Architect at Red Hat AI, is going to give us a deep dive into vLLM Semantic Router, a very exciting ecosystem project underneath the vLLM project on GitHub. Cedric Clyburn is going to cover the new vLLM course we have on DeepLearning.AI, which is pretty sick. So looking forward to that. So let's go ahead and get started. In terms of the vLLM project update, we're going to go over quite a few releases, some blogs, some updated docs, some, of course, model releases, and then cover the latest vLLM 0.23 release that happened just last week, I think. And after that, give it to our special topic speakers. We might have a break for the next office hours. We might have a new session. Stay tuned. We'll update the calendar when we book that up. But yeah, we're preparing for a busy summer, end of summer, lots of sessions packed in. But of course, if you want to propose any new ideas or show off some of your own work, please message me or Sasha to let us know what you'd like to show the vLLM community. So without further ado, let's get started. If you're not familiar with vLLM already, it's a very important open source project and ecosystem. Its simple goal is to be the most performant, easiest to use open source inference engine for large language models. And that purpose as an inference engine is really to support, of course, the hundreds of different model architectures that you're interested in running, the new ones that are releasing on a daily basis, implement the software abstractions to represent those models in a sort of shared library. And then, of course, make sure that all of the hardware accelerators that would like to run those models efficiently can do so. So, of course, vLLM gets great performance on NVIDIA GPUs, but also, AMD GPUs, Google TPUs, and many other, a dozen plus hardware accelerators plug into vLLM because it defines that software abstraction and the operations that each hardware vendor needs to implement in order to run these models. And this has resulted in vLLM being obviously a highly adopted and active open source project, given the size of the open source AI ecosystem. It's Apache 2.0 licensed. It's hosted in the Linux Foundation under the PyTorch Foundation. It's a simple Python-based library. You can pip install it. You can Docker pull it with images made on, CUDA, AMD, Intel, ready to go. It has a ton of GitHub stars. We get a huge amount of pull requests and issues submitted every day, and we try to merge as much of them as we can. It's a very actively used inference engine in production, of course, with millions of GPU hours that we know about deploying vLLM 24/7. So a lot of very expensive hardware runs this software. So a lot of people care about, obviously, the quality of it, and we're happy to oblige. We have a very active developer Slack, which you're welcome to join, slack.vlm.ai. And in terms of usability and understandability of all the latest models and hardware that there's out there, we've developed recipes.vlm.ai to guide you through whatever various model you want to deploy, whether it's on L40s or B200s or AMD MI355Xs. We can have recipes there for how we think those models should be deployed with different parallelism configs, different tool call parsers, et cetera, et cetera. I've already mentioned, vLLM has a ton of contributors. We have over 2,800 contributors from dozens of academic institutions and enterprises, frontier model labs, all contributing to the project, which is pretty amazing for something that's only around 3 years old. And then, of course, vLLM goes beyond the sort of inference engine itself. We have a very diverse project ecosystem that has grown around vLLM and the whole, inference end-to-end optimization pipeline. So we have like Guide LLM, LM compressors, speculators for optimizing, benchmarking your models, vLLM Omni for supporting multimodality output models, image generation, video generation, LLMD for distributed inference, managing your cluster scale deployments of vLLM, Semantic Router, which you'll hear about today, and many other things that are constantly growing. And then, of course, all the applications and ecosystem that rely on vLLM as the inference engine to go do their actual useful applications or reinforcement learning or et cetera. So that's the introduction to vLLM in a very brief way, as much as I can. Now I'm going to cover some blogs and releases over the past 2 weeks that's new. So we have this really interesting blog from the AnyScale team. They've been doing a lot of work to build out and improve the performance of vLLM deployed through Ray and Ray Serve. In particular, they published this blog on Ray and vLLM on AMD, but pretty importantly on pre-filled decode disaggregation, which is a really important sort of deployment style for inference servers at the production scale. It ultimately allows you to serve more tokens, get more throughput while meeting the same latency SLOs, which are important if you have paying customers. They want their tokens coming at even, steady rates. I just think even though this says AMD hardware, I think a lot of the learnings are applicable to any hardware. And overall, it does a good job walking through how do we think about traditional aggregated deployments. What is PD disaggregation? What are the tuning knobs? And I think especially one of the things that's not talked about explicitly enough is sort of this graph of what saying you're doing disaggregating, prefill, and decode is one thing. It's also a different skill to learn how to manage these deployments properly and understand the physics of the situation. Of you don't necessarily want the same number of GPUs dedicated to prefilling or decoding, depending on the size of your model, depending on the latency SLOs you have, depending on, most importantly, the workload you have. Are you having very large context, constant prefills? Are you doing a lot of prefix cache hits because you're doing agentic workloads? Making sure you choose and tune that ratio properly based on that workload is really key. And I think this is a great resource for learning more about that if you're curious. Another one I want to highlight, this is actually sort of docs that have been around for a bit. We have integrations with a lot of frameworks in vLLM, but I kind of wanted to highlight, of course, the popular coding agent ones. So if you didn't know, if you're curious to use open source models instead of maybe OpenAI models or Anthropic models, you can run your vLLM server with vLLM serve, Gemma 4, whatever, and point Codex or Claude Code directly at that endpoint running on your own infrastructure and start experimenting with open source models in the harnesses that you're comfortable with. Please check out these docs that we have for Codex, Claude Code, other integrations as well, like OpenClaw, of course, or Hermes Agent, or I think OpenCode and various other ones have them as well. Please let us know if there's issues with this, or if you run into issues with tool calling. We're constantly improving the quality of this and serving more and more billions of tokens to these harnesses through the vLLM server. We'd love to have obviously more people, more diverse applications running through these interfaces and make sure we make them as production grade as possible. So FYI. Next, we had, or rather, I'll get into a series of sort of important model releases. Minimax M3 is a really notable one, I think. obviously, the Minimax series of models have been really interesting in terms of agentic coding agent capabilities. I think one of the key things about this launch that are really cool is we launched at day 0 with a special trained Eagle 3 checkpoint. So very high quality speculative decoding for peak performance. We support the new type of sparse attention. It has this unique grouped query attention in a sparse way, rather than the traditional dense GQA, much like the sparse MLA that's implemented for DeepSeek V3.2 and GLM5. And notably, if you see in sort of this graph I had to cram in over here on Inference, we launched on day 0 across NVIDIA and AMD, and across all of these hardware platforms running vLLM on day 0, which is pretty huge. We have recipes, everything usual about this, but I would note that I recommend reading the vLLM blog specifically about this release, because there's a lot of performance work and particularly deep dives into the architecture for how we manage to implement this efficiently. It's a very complex architecture, and like I mentioned before, the sort of Minimax sparse attention, the MSA sort of small diagram here, is a very interesting, I would say, model architecture, software, hardware, co-design that is just simply interesting to read about if you care about the future of model efficiency, especially as now we're getting into millions of tokens of context. We really need these types of efficiency and attention. Next, Poolside released their largest model yet, Laguna M.1. Pretty straightforward improvement over their previous model. I think really formidable on its own, designed for agentic coding and long context as well. We have a vLLM recipe for it. I recommend checking it out. And hopefully we can expect more from them in the future. Next, probably one you've heard about a lot in the community is GLM 5.2. People are really talking about this as the latest moment in open source, where we have a model that's competitive with Claude Opus and GPT 5.5, as you can see by sort of these agentic coding performance by effort level, comparing GLM 5.2 versus Claude Opus. So yeah, I mean, it fits on a single H200 node, B200 node with really good performance. It pretty much slots in right away if you've been using GLM 5 or 5.1. There are a bit extra performance enhancements. Most notably, this sort of index share idea noted in the architecture changes here, where we sort of amortize the cost of the calculating the indexes for the sparse attention that this uses. This uses DeepSeek sparse attention, or sort of sparse MLA, as we call it in vLLM, so that we only need to sort of calculate the indices for like the tokens we want to reference in a sparse way for one layer, and then we reshare those for the next three layers, sort of amortizing the cost a bit and allowing us to scale even better, even as the model has a lot of layers and we scale to more and more tokens. So obviously, I think enough people know that this model is impressive, and reference implementation on its own of a frontier coding model. So yeah, we're just happy to keep pushing performance on this, training new speculators like a DFlash module. I hope we can have soon, various other things. And then a quick shout out that we are sort of doing a sprint right now for GLM 5 performance. You can check out the link here. We'll have a lot more work that we're planning to post up here, optimizing it on Hopper and Blackwell specifically. And we have a Sprint GLM 5 channel on the Slack if you want to sort of join the discussion, ask about things. I think there'll also be some stuff to expand it onto new hardware platforms as well. But in the case of at least performance on the leading ones, we still have clear work that we have to do post-launch. So yeah, if you're curious, follow along there, and also hopefully help out. Let us know if you find some bottlenecks and things that we can help with. Next, I wanted to cover another really great blog from the community. So Prime Intellect is a very cool company. doing a lot of different things in terms of a GPU cloud with efficient resource utilization, good pricing, most importantly, RL environments, and most importantly, their open source RL stack, Prime RL, is pretty formidable in the community on its own. And yeah, they released this awesome blog on how they do RL at the 1 trillion parameter scale, scaling models like GLM5, especially doing reinforcement learning at dozens, if not hundreds, of GPU scale using vLLM for the inference rollout part, which is sort of the dominating amount of compute during reinforcement learning, using all the latest techniques, optimized FP8, MOE kernels, router replay to reduce the trainer inference mismatch, doing wide expert parallelism, splitting this model across clusters of GPUs, and just all sorts of stuff that's useful also at the much smaller scale than 1 trillion parameters. But yeah, really just a great overview of what makes up RL at the sort of frontier scale, but also what are all the performance things that make it up, what are the structures and architectures, many more diagrams than the ones I have here. It's just yeah, a really interesting thing to look through, and yeah, kudos to the Prime Intellect team for open sourcing all of this. It's amazing infrastructure that we all get to benefit from. So yeah, appreciate it. So that's what's new in the community. Now I'm going to go over the latest vLLM release. It's a sizable one. Even in just 2 weeks, we had over 408 commits from 200 contributors, 63 of those brand new people merging code in vLLM, which we love to see. Some of the main focus areas are DeepSeek V4. We're still pushing a lot of performance there, integrating the latest TRT-LLM-gen attention kernels, enabling EPLB for mega MOE for better production usage beyond just benchmarks. We also have been pushing a lot on Model Runner V2, enabling it by default for more models. Hopefully we can enable it for MOE models soon. Integrating the most performant sampler we have with FlashInfer. We also landed, in this release at least, Gemma 4 unified support. So this is like the encoder-free multimodal version of Gemma 4, which is a really cool architecture. If you're interested in multimodal large language models, it's really cool to read about. Instead of separate encoders, it uses sort of raw patches from the image or audio data and projects that directly into the language model backbone. And also native support for Gemma 4 MTP, so you don't need to use the nightly anymore for that. Also, several other models, Step 3.7 Flash, Cosmos 3, the Reasoner part, Granite Speech Plus, JetBrains Mellum, their latest model in a while, which is really good for efficient coding. And yeah, a quick shout out to the Model Runner V2 pipeline parallelism optimizations. There was a big squash to remove bubbles and improve throughput for pipeline parallelism. And yeah, Nick on that PR, if you go check out the PR, he has this pretty cool animation sort of animating through yeah, how this works when you have 10 micro batches going through the engine with pipeline parallelism across four ranks, and how all these patches fit into the different pipelines in order to keep all the GPUs fully saturated. Really cool. Yeah, a good amount of improvements on AMD and NVIDIA. Finally, native weight-only quantization kernels on RDNA3. So greatly improving, like GPTQ, AWQ model compression on those GPUs. On NVIDIA, still lots of improvements on Hopper and for FP8 attention, for vision transformers, vision language models. The maturity of multi-tier KV cache offloading has gone along really well. Particularly, enabling hybrid memory allocator support, and most importantly, enabling a sort of mature offloading to not just CPU memory, but now disk or other remote storage. which is great to see. The Rust front end is also under active development. Lots of features coming in there to get parity with the Python front end. So hopefully in a month or so, we can start hopefully using the Rust front end by default. This is a great place to work in vLLM to help out and get some quick contributions. Just kind of translating Python code to Rust is a good starting point for a lot of this. We've also, landed the unified parser interface for reasoning and tool call parsing through one interface. There's not really a reason to deal with the parsing in a separate way. This has been in the works for a while. Great to see that land. A lot of optimizations for multimodal inference and generally, high throughput or really large multimodal items. Slowly working through those. On the EPLB front, we were using synchronous expert parallel load balancing. Now we finally tuned async where it can be the default. So this should see good improvements for large or really sort of any expert parallel deployments you have of large MOE models and some pretty benign dependency updates that you shouldn't need to worry about too much. Okay, that's all I'm going to cover today. Now I'm going to hand it over to Cedric to give us a little sneak peek on the new vLLM course and tell us what's in it. Take it away.
Yeah. Thanks, Michael. I appreciate it. Hey, everybody. My name is Cedric. I'm a developer advocate here, but I'm super excited to announce that we've got the vLLM course now live on Andrew Ng's DeepLearning.AI course platform, which is really big because for a lot of us who are now doing AI engineering or serving our own models, we kind of came into this as newbies, right? And we were learning what are model weights and what is KV cache and what are different types of hardware accelerators and how do they work differently with my model and quantizing the model to work on those types of hardware. So I worked with Andrew Ng and his team about 6 months ago to come up with the idea to create this course. And originally it was supposed to be on quantization. So what are the different algorithms and how low can you go to achieve performance with these LLMs? But we expanded it to go even further. So now it's a course that you can take for free on his site. So Andrew Ng, by the way, is the former head of Baidu's AI team, but also Google's DeepMind, which makes Gemini now. And so he's really adamant on, providing free access to AI education. And I met with him earlier this year to talk about this course. And he was like, I can't believe vLLM isn't on here already. So he's super excited about it. And he has a huge reach to kind of spread vLLM into the community and, make all the hard work done by Michael and the team here known for and known about, even beyond our bubbles and our circles here. So feel free to check it out. It provides kind of this pattern of optimize a model, deploy it on vLLM, and then benchmark it. And it uses all of the different projects that we kind of commonly see in the vLLM ecosystem, like LLM compressor in order to do GPT-Q quantization on a Quen model, and then also guide LLM in order to benchmark and do evals on the model that you deploy. And when I say model that you deploy, it's really cool. You actually get your own sandbox environment that, they're graciously providing a Jupyter environment lab to run a Quen model on CPU. And so a lot of the work went into creating those lab exercises, but also explaining how inference works, because even myself, I didn't fully understand. So I went and spent hours trying to visualize this, so that people could understand what happens during every step of inference, from the moment you send that query to the model inference server like vLLM to getting your result back. And I talked about how those different projects come together. As Michael introduced on the second slide of office hours, you've got all these different capabilities on top of vLLM for inference serving. And we show you how to quantize a model, but also how to serve the model with vLLM, see the metrics, and benchmark this. And it's really cool because I always wanted to show this, and I was like, how are we gonna give people resources to run these models if they don't have it themselves? And so now it's all in the cloud and it's free to use. So we spent a lot of time visualizing this, and I would love if you guys check it out yourself. There's a blog on it on the vLLM site, But also, thanks Sawyer in the chat for dropping the link if you're interested in checking out the course. It takes about an hour, hour and a half, but it's a lot of really good concepts. And yeah, I'm just excited to see it to come to fruition. Sasha and Michael and Sawyer were really crucial to me putting out this course because I could rely on them to kind of learn myself as someone who's new to AI engineering. And yeah, it's out there, free to use, so feel free to check it out. And yeah, that's all for me. It's a big exciting thing, but it'll be out there and it's totally free. So, you know, give it a try or share if you have friends who are new to vLLM and you want them to get started in the right way. So cool.
Yeah, very cool. Thanks for sharing, Cedric. And yeah, definitely people are excited from the seeing in the chat and the emojis popping up. So found your right audience. Yeah, well, let's go ahead and pass it over to our final special topic, going in detail. Christopher, take it away.
Yeah, excited to be here. My name is Christopher Newland. I was actually previously on Cedric's team up until a few weeks ago. So he and I have had a wonderful, about 3 years now working together. So it's awesome. He initially talked to me about that project, I think over a year ago. So it's been awesome to see how he's built it up and really hit a home run with it. So definitely check it out. Recently, I switched roles at Red Hat as the chief AI architect for North America. So as an architect, I'm really blending both the side of being a scientist and then also an engineer. So this presentation is going to tell you a little bit about what vLLM Semantic Router does, but then also how is that implemented? What are some of the concerns about it? And some of the things that I'm doing right now to help kind of alleviate some of those concerns when we start trying to implement it in practice. So I'll be talking about, like I said, the project, but also how we can use things like redaction and guardrails in conjunction with it when we start talking about some of those concerns. So a typical architecture that we see, especially as people are trying to roll out agentic engineering into their architecture, is having a variety of agents that are communicating with each other. One of the things that has been coming up lately is this need for this concept of semantic routing. In this case, maybe it's contextual, like you want financial information to go to a financial model that you have certain data around a certain harnessing. Maybe you have one that is doing sales data, or maybe you're just routing based off of cost management. You know, you're sending things to SaaS models if they make sense, but if it's something a local model can handle, route to that one instead. What happens, and one of the biggest things that is challenging with this, and this is where you know, even when using something like vLLM Semantic Router, is once you go past this, what we call this trust boundary. And that's because projects like Semantic Router share context between that local model and that external. And it may be that certain data we don't actually want to cross beyond that trust boundary. So just to kind of give you an idea of some of the things that we're working on here at Red Hat, that gets more into the practical side of some of these tools. So this is where we're looking at sensitive data like John Smith's salary is 185, calculate his bonus of 15%. This might be a simple thing for a model to do. And if we were just using semantic routing, it might go to you know, a model that it would otherwise shouldn't. But we do want to catch information like this. This definitely becomes really important when we start looking at different compliance with things like GDPR, HIPAA, other international regulations where we need to prevent data leakage and PII from escaping certain bounds. But we still want to take advantage of things like semantic routing. And these are things that we can do in conjunction with vLLM Semantic Router when we start actually deploying it in practice. But with that, let me kind of talk a little bit more about some of the challenges. You know, this gets more into topics like data sovereignty, as I was mentioning before. You know, we talk about PII. It may be used for unnecessary spin, where we want to route to, like I said, maybe external models for only certain complex tasks, and then actually do local models for anything that would be within the range of that model to handle. And this is actually where I think most of the community around vLLM Semantic Router is focused on, is this unnecessary spend segment. So this is where there's a lot of publications. I got a couple blogs out on this. I know the vLLM Semantic Router webpage has a few things out, and some of the examples they have are specific to this category right here. But let me talk a little bit about what the Semantic Router does and how it solves this. There is an embedding model that does a semantic classification. So it inspects the actual context. So this is different than, say, some other routing tools that may just be looking at headers or different types of session flags. This is actually looking at the context of the actual prompt to the model. If you're familiar with the LLMD project, the technology idea is similar. What they're doing is different, though. And for LLMD, if you're familiar with it, it's looking more at the KV cache and the prefix to determine where it routes, where this is actually looking at the semantic classification of the full context. So it's actually looking at a similarity of the embeddings for some what we call anchor. The anchor would be a series of questions that we've already given the semantic router to do its routing. So a classic example would be, what is the capital of France? And if we're routing between a frontier model and a local model, you could probably say that the local model would be able to handle that question very easily. So that's a case where we might set an anchor, which would be an embedding that it matches against, where we say that type of request we want to route to the local model. So this is using a few different technologies to accomplish this. For the embedding, we have the MMBERT 32K. This is something that there are opportunities to kind of swap out different types of embeddings, but this is one the community has really kind of focused on. This also uses the XProc, so when we start getting into things like the EPP and things like Envoy, this is what then handles that routing layer once we get the determination back from the XProc. So to kind of put this together, we have a request. It could be coming from an OpenAI type of API request, not limited to that, but for this example, they would go through an Envoy. The Envoy would check with this particular EPP, the XProc, and that is where the semantic routing process actually lives in this case. And then that would then determine which route it takes. Is it going to go to an external model? Is it going to go to a local model? Is it going to, and you're not limited to that. It could be any location. As long as there is an API on the other end, you can be routing off into the next destination. So just to give you kind of an idea of what vLLM Semantic Router does when we actually start looking at this from an application standpoint. So for my local, so I got really involved in this project last fall. And the reason why is because I was starting to experiment with some of the early agentic loop agents. So I was doing some experiments over December on things like OpenClaw. Once it was released, was gaining some popularity, and then things like LangChain and some other implementations. And the problem that I had was that I was running out of tokens, especially per minute. So within our organization, we use Gemini, and I was using an API key, which I had unlimited token usage, but it was throttled per minute. And it was making the experimentation very difficult. So one of the gentlemen who actually was one of the creators of this, human, who was a colleague of mine here at Red Hat before he moved to Microsoft, I approached him about this problem. He's like, "Oh yeah, this is, I'm working on something that will solve this for you." So I got to get involved with this pretty early on. So my use case was routing between my home lab, where I have currently have the 35B Quinn 3.6 MOE model on it, and then routing between that and then this Gemini instance that I'm using as a SaaS solution. And what I actually found was about 80% of the traffic was going locally, and I had really pleasant results. So I kept up with the project, and since I've applied it to a lot of different areas. One thing that's really crucial is this confidence score. And I think that's where sometimes there's some confusions. Sorry, double click there. So from a confidence level, the embedding will, when it does this analysis, it will come back with a confidence score about how confident it is that the request coming in is like the request within the anchor. So you may have a request like, what is the capital of Germany? And the hope would be that would have a very high confidence to the original question of what is the capital of France. This gets a little bit more challenging when we start talking about some more complex type of requests, especially when we get into agentic or software development. But the hope would be that we're getting these confidence scores as high as possible. So one suggestion I can give you if you are exploring semantic routing is definitely go back and evaluate your confidence scores. This is where I see a lot of failures when people are trying to adopt this project, is that they're not checking these confidence scores and adjusting their anchors and the tuning of the model appropriately around those confidence scores. But this is an example of what I was doing locally within my own home lab. And this is just a visual example of kind of what that looks like, where for me, I was doing it as simple, medium, complex, and reasoning. These two right here went to my home lab, and then complex and reasoning went to the external. I did it in 4 categories because I recognized in the future I might want to even expand this even further. It may have more than just 2. So I wanted to have the anchor set there where I'm seeing the correlation there between the different anchor sets. And these would be those 4 categories. So when I initially did this, I had about an 80% success rate, and I defined that as anything that either was misrouted based off of a training set that I created separate of this, and then also based off of those confidence scores. So I actually have another blog post that I just released on semantic routing. That could be a whole another 30-minute, hour-long talk, but I actually went through the fine-tuning process of actually fine-tuning the specific model that I was using for the embedding process, while also using synthetic data generation to expand on my anchors. When I actually applied that process, I got the success rate of my training set, my validation set, all the way up to 98.5 once I introduced some of those methods into this process. So that's just a way of trying to identify the ways to adopt this, because a lot of times people just want to pull down these projects and have it work out of the box on day one. One thing I would say about semantic routing is it's something that you're going to have to provide your own domain knowledge towards. You're going to have to understand the type of use cases that are specific to your routing, and how you can then kind of fine tune that with a few different techniques with the anchoring and then also some more traditional fine tuning approaches. Ultimately, when I start moving this into working with our customers, it starts breaking down into really like 4 quadrants of what is internal, what is external, and then also what's highly sensitive and what's not highly sensitive. So we end up having this type of matrix where we're starting to look at semantic routing from, excuse me, I think I have it. Is it coming through? Yes, it is. Okay. Sorry, I have a bar here that's covering part of it. So for this is where a lot of our customers at Red Hat are having concerns. And the reason why this happens is because when we start looking at semantic routing, we share context now between multiple models. We're routing some of the context to a local model. We may be routing to a less isolated model within our own organization. or we may be routing all the way to a SaaS model where there's a lot of regulations involved. So we start actually looking at this more as a matrix rather than like a one-dimensional issue here. So for a particular customer I was working with on this, I defined it as those key matrix quadrants that you saw earlier. What's public, what's internal, what's confidential, what's regulated, and then obviously we'll have a set here what's called never egress. And that gets more into things like guardrails, which I'll show an example of here in a moment. So if we actually put this out as a table, this lets you see like the type of the routing that we do in this case. Now, this particular customer that I was building this POC for wanted to use redaction instead of just block the request. So there were a few cases where they wanted to just strictly block the egress, but there was other cases where they wanted the question to still go out because it would still be functional, but just remove any like PII data or anything that would be identifiable to that PII ultimately. So we use actually redaction here for some of these, and also we would then have like a never category, which only routes locally to an isolated model. If we look at this from like a flow diagram, in this case, we have this local model. So my example would be like a Quinn 3. We go through the classifier and then the semantic router. The classifier is what's actually doing the semantic analysis. And then here, for anything external, we go through a redaction process. I'm using Pseudo and Gliner in this case. I think one of these is a Microsoft project, and I think one of these is just an open source. I picked these because this is what the customer was interested in, but there are a few different types of text redaction tools out there that work really well for this. So that's something, if you want to reach out to me on Slack or by email, if you have some questions, feel free to ask, because that's a whole different field on its own. But I was using these type of redaction analysis tools in conjunction with the semantic router in this case. What I tell people is that the semantic router is not a guardrail. It should never be used as a guardrail. That's not its functionality. It's meant to move very quickly. It's not meant to do the deep type of analysis that a guardrail is doing. You can use it in conjunction in the case of this, where the semantic router is also doing the analysis for sensitivity, but you also want to have that guardrail at the end that's actually doing the final look through based off of your organization's requirements. Guardrail is something I could go into a whole another hour, 2-hour long conversation, but just know that this is usually a much stronger LLM that's doing the analysis to determine if the context is something that should be able to go beyond the trust boundary or not in this case. So always combined with, in this case, like a good guardrail. And the example that we're doing with our customers right now is Nemo guardrail, which seems to have a lot of popularity right now. And then obviously at this point, we go past our trust boundary. This is where it should be redacted. There should be an analysis. You also want to make sure that you're having good audit logs, you're having good trail there, so that you can always go back, and if something does go wrong, you can always go back and kind of reevaluate it. When we put this all together, this is where we would have some type of input. We have the classifier, the redaction, egress, and then ultimately we go external. When we look at this kind of side by side, we see here we've got kind of this flow, and then here we go from Jane Doe to person 1, and then we have staging to cluster 1. Some examples of what that type of redaction looks like, which is a very powerful tool when we start combining with this type of semantic routing. So ultimately, we start looking at this from layers. We have the different application layers that have different guardrail services attached to them. We look at it from an egress side, where then we have the Nemo guardrails So you don't just have to do this at one layer. You could expand this. This is where things like policy engines could come into play. OpenShell from NVIDIA is very popular for isolating the actual runtimes for some of these types of agents that kind of can work in conjunction. There's a lot of ways that you can incorporate some other tooling in this to kind of expand this kind of multi-layer approach. And then if you're using something like Kubernetes, you have the option for things like network policies that can isolate those egress points even further. So I get concerned when I do this 100% because I did show this to the customers, because anytime you tell an enterprise customer something's 100%, then it becomes contractual. They'll be like, that guy told me it always works this way. So these are my benchmark results. So I use synthetic data generation to generate about 1,400 different types of anchor questions, with then showing the results of that. I took about 20% of that as my validation set and used the other 80 to then do the fine tuning. When I incorporated that other 20% back into this pipeline, this full type of architecture, I was able to get it to the point where I was actually getting 100% of the time. Now, obviously, in a full enterprise test, if we were to expand this to maybe tens of thousands or hundreds of thousands of types of infiltration points, I would imagine that this would be closer to like 5 nines, an industry term for like 99.9999. But what I wanted to show this particular customer is that 5 nines was possible with this type of configuration if configured correctly. Another thing that you can do is have this in conjunction with something like LLMD. I think there's a lot of ways that these architectures, these projects work together in a single architecture. So this is an example of what this particular customer was actually doing ultimately, was then using LLMD to then, after the contextual routing happened, then the prefix-aware caching happened in a similar type of route, where we wanted to make sure that we reuse the cache that was available from the KV cache in the correct location. So if you're not familiar with LLMD, definitely check out that project. It's spun out from the vLLM community, a very powerful tool for handling distributed inference and a fleet of models through an inference if you're running that type of configuration. But this is just an example of what that would look like then if we were to apply semantic routing with something like this. So you're not limited to one type of router, especially when we start talking about Envoy. These are very lightweight routers compared to like the heavy F5s of the world. They're meant to be kind of daisy chained like this in a lot of ways when you start configuring them. So this is a pattern that works really, really well if you are using something like LLMD internally for your distributed inference. If we put this together from an architectural diagram, this is kind of what this looks like. This would be just an example if you are running like your own models as a service within your organization and had like an LLMD load balancer / distributed inference. This is kind of what that could look like then when we kind of put all these pieces together. We have a variety of agents communicating within the within their own namespace, isolated to that particular namespace. And then they have the ability to reach out through the gateway in this case, which then will provide some type of tooling with the semantic routing. In this case, I've set up the vLLM Semantic Router for this particular customer. And this shows you where sometimes it would go to the enterprise SaaS solutions, and then other times it would route into this mass service, which has LLMD and vLLM running for each instance of, in this case, a Nemotron 3120B that this particular customer was experimenting with. And then off to the side, I also have these redaction services, which are the tools that then do the redaction when sending externally. So this is a way that you could combine it all into a single architecture, have all those services available, and then actually see vLLM Semantic Router in practice, and what semantic routing can actually look like when we actually combine it with some other industry tools to kind of give the full big picture and what this looks like end to end. I do have some news about Semantic Router. The Semantic Router has been incorporated into Agent Gateway upstream. So if you want to know more about this, there's some news articles on the vLLM Semantic Router website that highlight this. But now Agent Gateway now is incorporating vLLM Semantic Router as an optional routing tool within its gateway. So this is really cool because we're seeing. I have been playing with this project now for about 5-6 months. So I'm pretty intimate with how it works, but you can see that I've done a lot of work towards this. I think Agent Gateway incorporating vLLM Semantic Router is the first step into us getting kind of an easy button for deploying these type of things within a standardized type of gateway configuration. So if you're using Agent Gateway or you're exploring using an open source project for your gateway needs, Agent Gateway is a great one to check out for that integration back into vLLM Semantic Router. So definitely check that project out if you have any interest. So I have a demo. So this is actually connected to my home lab. My power was taken out this morning for a brief moment. So you're kind of praying that your home lab comes back up right. But I did check just a few minutes ago. So I think we're all good here. So let's just do what is the capital of France. We'll do an analysis of that. This is a case where it says this is public, it's simple. In this case, it's just saying like let's just route it. Like it's not of any concern. Egress approved it, and then we move it on its way. If I do something a little bit more confidential, so draft a performance improvement plan for John Smith. And if we try that one, we'll see that's confidential. It needs to be redacted. So we have somewhat complex, confidential, and then you can actually see the redaction that happens here. So this is actually hitting the API within my home lab. So you can see how this becomes this. You see person one and then money one here that's been replaced in this case. And all that's being managed by the semantic router. So the semantic router decides where it needs to route to. I have this matrix here. And then I have a variety of other ones. There's another one, good one here. There's another one. This one's based off of like a CVE, and it's basically going into information that this is an example specific to a customer I was working with. They didn't want their internal exploits going externally. And this is a case where the egress picked it up first. So this is where the complexity was medium. And then it determined from an egress standpoint that it shouldn't go out. So it rerouted it. This is a case where it starts out as something that might go external, and then the egress sends it back to this particular local model based off of this this type of index. So that's an example. That's it for my presentation. I will be providing this in slide form. Obviously, I won't include the demo since it's interactive, but I will include all of the slides I have here. And then I will include also some of the links I mentioned as well in that slide when that becomes available. So I think we have a couple of minutes. I do need to drop at the hour, but I don't know, Michael, do we have time for questions?
Yeah, definitely. Yeah, really cool series of demonstrations, slides, and everything. Yeah, it was a great overview. Yeah, there were some questions that looked particularly interesting. Yeah, sorry, I missed. Well, yeah, I mean, I guess maybe the latest one from Gerald, how does it handle large input tokens, like when you go to the 100K tokens or very large amounts, I guess, like maybe routing or streaming?
That's a wonderful question. So that did come up in our POC, and it also came up at my home lab. What I eventually had to do is keep an index of all of the context, and then I had to do an analysis off of the full index of the prompts, and then I would only have the actual semantic router analysis go off of the most recent addition to that. So there are ways that you can kind of compare the both, but you're correct. When you start getting into like 100K or like anything 100K plus, even like 50K, 60K plus, the semantic router will start breaking down. So you have to kind of break it down into its smaller contextual parts, basically what's the most recent, because that's actually what is the most important. When you start talking about streaming, that's where you would have to have some type of blocker that's actually evaluating that streaming in blocks, because otherwise, from a real-time analysis standpoint, we experimented with it. We got it down to 40 milliseconds with this by kind of tweaking some things, but even at 40 milliseconds, we were having trouble keeping up. So we would end up having a queue that was keeping that new contextual flow, but it then just started overloading. We saw it building up a little bit too fast for the actual use case that this customer had. So that is definitely an area where there's challenges. I wouldn't say it is impossible, but it just wasn't something that within our POC that we saw any meaningful results from.
Yeah, for sure. That makes sense. I think like one other thing that kind of makes me question is like how this should work, or think about like I guess like workloads or requests that have a lot of like prefix cache like hits, like agentic multi-turn. Like maybe it'd be a bit weird if like you're doing like one session to the endpoint and then like suddenly you get routed to a different model deeper in the conversation because the semantic router decides a different model should do this. Both from, I guess, like a cost perspective, latency perspective, and maybe third, like model response or accuracy perspective. But you could say like that's kind of guardrails, like it should step in at a certain point. Yeah.
We did see some issues in that area. So that it was another issue that came up. So what we tried to do, that's why I had to index the context, because we had to still send the full context after the initial analysis. So the analysis only did the most recent, most important context, but then we still had to attach the full context back. But even then, there were some things that we identified from a caching standpoint that could be a challenge. So that is a drawback of it. And I think that's something where probably more research needs to be done from the community. This could be something where some of the things that we're doing with LLMD, Michael, could be incorporated, where there's some more opportunities for how the KV cache is managed if we incorporate more semantic routing. But that is a challenge that we see, especially like you said, when we start looking at agentic looping, where there's a lot of repeat and opportunities for KV cache optimization.
Yeah. I mean, great answer. I know you need to go, but just one more question.
Yeah, no problem. One more.
Ben Browning, how does it decide if redactions change the semantic meaning or ability to answer a question? Thinking about an agentic flow, the model will see different data than the harness. So will this break the feedback loop between the harness and the model to solve a problem when they're seeing different data? I think, again, kind of in this agentic loop case.
Yeah, so that was something that I had to incorporate into the anchor training. So there was a series of questions that had to do about when to route to the redaction route. And so we do not feed that back in, because that adds another layer of latency that we just don't want to deal with, at least for this particular group that I was working for. In this case, the redaction was only doing things like really like nouns, like a person's name, money, social security number, a key to something within like a code base. So what we found was that didn't change the context in any meaningful way once it was actually ran through and returned. The only thing that was a challenge was that in some cases for like coding bases, it would obviously input in like key 1, key 2 back into the code base, where you would then have to figure out a way to wire that back up to whatever the initial key was. Obviously, you could do some type of injection if you're doing config files in a good way, and that was what we eventually set them up with like a Jenga type of thing for injecting that back in. But that was the only thing that we saw, was that, you know, contextually then it was when it came back, you would then have to find a way to undo the redaction. And there are ways that you could do that with the redaction tool, but we didn't get to that point. And they didn't seem too concerned about that. They were more concerned about just catching things before they got out from that trusted boundary.
Yeah, maybe for the specifically latency perspective, we can include speculative decoding there. That may kind of improve the model's performance, having one large and one a teacher and a student model.
I know that's something that we explored, especially with the guardrail. I think that's kind of too early to see what those results would be. But obviously, that's the type of optimization that we'd be looking at by taking this from a POC and moving it into like a production pilot.
Cool, thanks.
Cool. I do need to drop, but thank you everyone for having me. As I said, you can reach out to me on I'm on the vLLM Slack channel as well, so you can hit me up there, or feel free to hit me up on like LinkedIn as well. I can get back to you if you have any questions I wasn't able to get to. So thank you for having me.
Yeah, great. Thanks so much for coming. Just a quick answer, just because I see it before I go. Gerald, about how spec decoding works for large context, large amounts of tokens. It's yeah, I mean, I will say generally the sort of Eagle, DFlash, whatever speculators are generally trained on like shorter, I guess, context lengths or sort of samples, not like deep reasoning traces. This is starting to change, obviously, because more workloads are running at longer context lengths, and we want to better align the speculators with that. So that's something we can solve with, various methods of like, sequence parallelism or, like ring attention on the trainer side to make it more efficient at long context lengths. Yeah, at least from the inference perspective, if you fix the acceptance length and say you're able to predict the same quality of tokens at small contexts or larger ones, speculative decoding actually offers a greater benefit in terms of inference optimization at those longer context lengths. Because if you think about it, you're generating one token at a time and you're needing to read 100 tokens of context for each additional token that you're running. Or each token you're generating, right? In speculative decoding, you try to speculate maybe 5 tokens at once, and maybe you get 3 of them right. That's 3 tokens you're predicting for one read of those 100,000 tokens in cache. So at those long context lengths, where the long context KV cache can start to sort of compete in memory bandwidth with the weights of the model themselves. The math actually means, spec decoding can actually like speed up even high throughput long context workloads, because reading the KV cache from memory becomes the dominating sort of item. Yeah, definitely to say spec decoding is maybe even more important at longer contexts. And that's a part of the reason why like a lot of the recent research and what we're doing in speculators is to improve the quality of these speculators at long context, so we can get the same sort of acceptance lengths. Yeah. Okay, we'll call it there. Thanks so much of you for sticking around for the whole time and extra here. Great to see you. We will, I confirm now, take a break on July 9th, but we should be able to be back on July 16th with a very special guest. And yeah, stay tuned and stay involved in the community. Hope you have a good little summer break, and see you soon.